All right, today we are jumping headfirst into the Python Data Science Toolkit. We're going to unpack the essential libraries that data scientists rely on every single day to take raw, messy data and turn it into some seriously powerful discoveries. So it all starts with this one big question, right? How do we actually take a giant sea of information, numbers, text, images, and find the valuable insights that are hiding deep inside? Well, that's the core mission of data science, and lucky for us, Python has an incredible set of tools to help us do just that. So what even is data science when you get right down to it? Well, there's this famous idea from Drew Conway that just nails it. It's not one thing. It's this perfect intersection of three key skills. You've got statistics, so you can actually understand the data. You have computer science to process it all. And then, and this is crucial, you have domain expertise, which means you know enough about the subject to ask the right questions. When you mix those three together, that's when you start getting real-world answers.
Okay, so the very first tool in our toolbox tackles a fundamental need, the need for speed. Before we can do any kind of fancy analysis, we have to be able to crunch huge amounts of numbers, and we have to do it fast. This is where NumPy comes in. Think of it as the high-performance engine for all of scientific computing in Python.
Now, to really get why NumPy is such a big deal, you have to understand this trade-off. A regular Python list, it's awesome. It's super flexible. It can hold numbers, words, anything you want. But that flexibility comes at a cost. It slows things down. A NumPy array, on the other hand, is strict. It only wants one type of data, usually numbers. But by giving up that flexibility, you get absolutely blazing speed in return. So here's the secret sauce. Standard Python objects have a lot of extra information attached to them, which creates overhead. NumPy just strips all of that away. It packs the numbers tightly together in memory, which lets it perform calculations on entire arrays all at once, using the raw speed of lower-level languages like C. This efficiency, this speed, is the bedrock that the entire data science stack is built on. So now that we have NumPy taking care of the speed, we can move on to the next big problem. And believe me, it's a big one. Real-world data is almost never clean. It's usually a total mess of missing values, weird formatting, you name it. Taming that chaos is a job for our next tool, pandas. Just take a look at this. This is a classic example using data from the Titanic. And right away, you can see the problems. We've got missing cabin numbers, those weird NaN things. We've got numbers and text all jumbled together. If you tried to do any math on this as is, you'd just get a bunch of errors. It's basically unusable. And this is where Pandas just swoops in and saves the day. It gives us this really clear step-by-step workflow. First, you load your messy data into a special structure called a data frame. Then Pandas makes it super easy to find all those missing values. From there, you just decide what to do. Do you fill them in or just get rid of them? In just a few lines of code, you can turn that chaotic mess into something clean and ready for analysis. And here's the after picture. Look at that. The problematic cabin column is gone, the data is all neat and tidy, and now, finally, we can start asking the interesting questions. Like what factors actually influenced whether a passenger survived or not. That's the real power of Pandas. It's the absolute workhorse that gets your data ready for the main event. Okay, our data is clean. Now for the really fun part, discovery. The goal now is to dig in and find the patterns, the connections, the outliers. Basically, the story that's hiding inside all those numbers. And more often than not, the best way to find that story is to actually see it. For example, let's say we have this big table of marathon finish times. It's just a wall of numbers. Is there any relationship between how fast someone runs the first half of the race and their final time? I mean, you could stare at these rows all day, and it would be almost impossible to tell for sure. But the moment we plot this data using a library like Matplotlib or Seaborn, boom, the pattern just jumps right out at you. It's suddenly so obvious. You can see this really strong relationship. The darker areas show where most of the runners are clustered. In one single picture, we've learned more than we could have from scanning thousands of rows of data. And it's not just for simple charts either. Visualization can uncover really complex geographical patterns. Here, we're turning boring old latitude and longitude numbers into a vivid map of population density in California. This is how you get those aha moments, by turning data into a picture. So, finding patterns is amazing, but what's the next step? Well, using those patterns to actually make predictions. And this is where we enter the world of machine learning. Our guide here is going to be the incredibly powerful scikit-learn library. Let's think about a classic machine learning problem. Can we teach a computer to recognize someone's handwriting? To you and me, it's easy to see these are numbers, but to a machine, each one is just a grid of pixels, a bunch of numbers. We need a way to teach it to look at those pixels and predict the right digit. Now, that might sound incredibly complex, but the absolute beauty of scikit-learn is how simple it makes the process. It doesn't matter how complicated the algorithm is behind the scenes, you almost always follow the same 3 steps. 1, you choose a model. 2, you fit that model to your data, which is just a fancy word for train it. And 3, you use that trained model to predict answers for new data you haven't seen before. It's this elegant, simple pattern that makes machine learning so accessible. And once we've made our predictions, we can check our work. This chart is called a confusion matrix, and it's basically a report card for our model. That bright diagonal line shows all the times it got the answer right. Perfect. But what's even more interesting are the spots that aren't on the line. You can see exactly where the model got confused, like when it thought a 9 was a 4. This isn't just a grade. It's a roadmap for how to make our model even better. And with that, we've actually gone through the entire data science workflow. We started with raw, messy information, and we ended up with a working predictive model. Every single stage of that journey was powered by a specific, powerful tool. So let's quickly recap our complete toolkit. Each one of these tools has a critical job. NumPy is the engine, giving us the raw speed we need. Pandas is the workbench, where we clean and shape our messy data. Matplotlib and Seaborn are our storytellers, helping us see the patterns. And finally, scikit-learn is the oracle, using those patterns to make predictions about the future. You know, each of these tools is powerful on its own, but when you put them all together, they create a workflow that can answer almost any question you can think of, as long as you have the data. So the real question isn't about the tools anymore. It's about what you're going to do with them. What questions will you answer?